Now we look at the idea of a basis. So this just combines the two ideas that we were looking at in the previous chapter. So we say that a list L is a basis for a vector space V if and only if it satisfies two conditions. We need that L is linearly independent, and we need that L spans V. Okay, so for example, we have the standard basis. So the standard basis for Fn is going to consist of the vectors that have a 1 in one slot and zeros everywhere else. So 1 and then zeros out to the end, and then 0, 1, and then zeros out to the end, and so on and so forth. So the very last one in the list would have zeros everywhere except in the final position, like that. So that's the standard basis of Fn. The standard basis of the polynomials of degree m, that's going to be just the monomials. So 1, which is the same thing as z to the 0, z1, z2, z3, etc. up until the last one, zm. Let's look at other examples. So if I have the vector 1, 2, and I have the vector 2, t, this is going to be a basis for F2 for any t which is not equal to 4, which is the one value of t that would make the second vector into a scalar multiple of the first, and hence the pair would not form a linearly independent list. Let's see what else we got. So if I take L1 to be -1, 2, 2, comma 2, 1, 1. So this is my example from video 2.A.1, if that looks familiar. Then this list is independent in F3. But not a basis, because I showed in that previous video that 8 minus 1, 1 is not in the span. And in fact, any vector that has different second and third coordinates is going to not be in the span of that guy. If I take L2 to be L1 adjoin the vector 8 minus 1 t, then this one is a basis for any t that ensures that L1 is not in the span of the first two. So that means that t is not equal to 1. And so if you look at it, you'll see that 8, -1, -1, right? So in the case when t is equal to -1, I can solve the equation of having this new vector equal to a linear combination of the two others. And I'll let you work out what those coefficients would be in the case when t is equal to -1. All right. So the last thing to say for now is a proposition. So this is numbered 229 in the book. So if we take a list V1 up through Vn, this is a basis for V if and only if for any element of V V can be written uniquely as a linear combination of the given purported basis. And so the proof for this one, there's nothing to prove, it's just definition translating. So the fact that it can be written in this form, in other words, that a solution to this equation exists, that is exactly the same thing as saying V is in the span of L. And the fact that representation is unique, that is exactly the same thing as saying L is independent. So since a basis is exactly something which is both linearly independent and spanning, that follows immediately from the definitions.